So we're going to look at some guidelines and details going along with the two-sample t procedure, two-sample t test, two-sample t interval, which is talking about the difference of the means of two populations based on a sample taken from each of the populations. So here are the guidelines. And all across statistics, there's rules of thumb, I guess I should say, that have been adopted, sometimes based on simulation results, to see the kinds of things that go wrong and see how you can avoid them. And part of that is supporting what we see here, that simulation shows with distributions that aren't normal, you can get away with using the t-distribution if you follow these basic rules. So what we say here is that t procedures tend to be robust. Robustness, if you think about what robust might mean to you ordinarily, robust means like sturdy, right? And so robust in statistics means it's tolerant of deviations from the assumptions, that it still gives you accurate results, even if the things that are underlying the derivation of the process aren't strictly speaking met. The results of the process still are valid. So here's what it looks like. It says even if the sample sizes are as small as 5 each, as long as the distributions have similar shapes and no outliers, we can use the two-sample t procedure. Similar shapes, no outliers. So maybe they're skewed in one direction, skewed in the same direction. Maybe they're both bimodal, similar shapes. So you can just look at a histogram of the data. If they seem to have similar shapes to them, and you have tiny sample sizes, you can go ahead and use t. That's tiny, 5 each. For slightly larger sample sizes, so bigger than 5, I guess, and if the sum is less than 15 and they're about the same size, so they're maybe that's 7 and 8, or maybe 6 and 9, something like that. Oh, less than 15. Okay, so you don't have that much option. So slightly bigger than 5, and approximately equal, and less than 15. Okay, so maybe 6 and 7, it's less than 15. Maybe 6 and 8, something like that. So still pretty tiny. And if they're about the same size and they're between 10 and 15, without outliers or skewness, in other words, they don't have to be normal, they just have to no outliers or skewness, you can still go ahead and use t. And then as the sample sizes grow, here we have between 15 and 40, roughly equal. So maybe that's, pick a number, 10 and 12 sitting here. That's a lot bigger than 15, less than 40. Roughly equal sizes, the sum is between 15 and 40. Roughly equal sizes, no extreme outliers or strong skewness. It could have outliers or skewness, not strong skewness, and less skewed in the same direction. So that kind of comes back to this. Similar shapes. Here we're talking about skewness. Strong skewness, if it's skewed in the same direction, even though it could be fairly strong, if you're in that size range for samples, you can use the two-sample t-test. And then for n1 plus n2 at bigger than 40 with each at least size 15, it almost always works. So if you have a histogram of your data, you don't see something crazy going on. I suppose if you put a big enough outlier someplace, you can always throw things off, but those things don't happen in practice. So ordinarily, unless there's really a huge mistake in the way the data was collected, this is usually going to work. If n1 plus n2 is at least 40 and each is at least size 15, almost always works. So you have to use a little bit of professional judgment. This looks like such a very strange shaped data set. If it doesn't, then go ahead and use the two-sample t. Other considerations. If you're setting up an experiment, equal sample sizes are preferred. That means with equal sample sizes, the test works better and the confidence interval works better. So the test will be more likely to reject the null hypothesis if it should be rejected, and confidence intervals will be smaller if you have equal sample sizes. So you get more information if you have equal sample sizes using the same amount of data. Using the degrees of freedom to be the smaller of one less of the sample sizes for each of the groups is preferred for non-normal data and small samples. So though that degrees of freedom tends to be a lot smaller than the formula degrees of freedom, and what that does is make confidence interval wider and makes hypothesis test less likely to reject the null hypothesis falsely. So it's a conservative estimate. So you want to show there's something has happened. If you use that degrees of freedom, you're less likely to say something happened when it really hasn't, and you're going to get a wider interval where you think the true difference of the parameters lies. And that's preferred with small sample sizes, because with small sample sizes, you really can't be sure you are sampling from a normal distribution at all. You don't have as much information about where the data came from, and so you want to be conservative with what you do. So back here, when the sample size is 5, probably we're going to use degrees of freedom 4, etc. The formula for degrees of freedom looks like this. So for normal data, this degrees of freedom calculation is quite accurate in determining which version of the t-distribution your computed statistic represents. So it's a pretty complicated formula. We saw on the calculator that we had like a 25.6 as one of the degrees of freedom. And the calculator has a way of interpolating between the degrees of freedom of, like, it was 25.6 between 25 and 26, and deciding what the critical value looks like and what the tail probability looks like for that strange degrees of freedom. It's not even a whole number. So you're going to use that as long as you know you're sampling from normal data, or I suppose, or with larger sample size. Larger samples. Larger samples kind of force the sample means to be normally distributed. Of course, with really large ones like here, it doesn't really matter what you do, because you're going to get a degrees of freedom that's pretty large, and then the t looks like a z. So with giant degrees of freedom, t is z no matter how you did it, and you don't even care about the degrees of freedom anymore because it's a big number, and that big number causes t to be basically the same as z. So it's, if you want to use this to discriminate, it's probably just with the larger size samples. Maybe maybe you're close to 40 with n plus n1 plus n2, and maybe you're pretty sure it's normally distributed, and then you could use this and you might get more accurate results. It says here, avoid using the pooled option on your calculator. And yeah, sure, so we saw that in the calculator. The pooled option is computing this estimated standard deviation, assuming the standard deviations of the two populations you're sampling from are equal. If they're not equal, using the pooled estimate gives you poor results. If they're not equal, if they are equal, and using our standard error calculation that comes without using the pooled option, you get pretty good results. So the point is that in all cases, the way we've set up the t-distribution, the t-statistic for two-sample t, it works pretty well in all cases. The pooled option works slightly better if we know the population standard deviations are equal, but usually we don't know that. And so if we're going to go forward without that information, we'll use the two-sample t-test that we've described and the two-sample t interval that we've described. So basically, we don't use the pooled option. And that ends this slide.